Okay, okay.
No, that's a compliment. Thank you.
It's like the north for the ID.
Sometimes people say the opposite to me, like they say, I am a professor, but I'm a PhD. I don't know how to react to that.
Hello, welcome back everyone. Right now we are very fortunate to have Sewon Min, who is a professor here at UC Berkeley. And she works on language models, machine learning, NLP. And today she will talk about open language models for flexible data use.
Thank you for the introduction. Hi, everyone. I'm very excited to be speaking here in this workshop. Thanks, organizers, for organizing this. And yeah, I'm very excited to present our work last year called FlexOlmo. It's an open foundation model for flexible data use. Oh, can everyone hear me, by the way? Okay, cool. And if you have any questions, please feel free to ask during the talk, since I'm very happy to take questions in the middle. Cool. So I'll get started. So I work on foundation model and large language models. And as you all know, foundation models has benefited a lot from scaling in the recent years, in particular from scaling the training data, the data that you can use to train a model. So one interesting question that we should all think of is, will we continue to benefit from scaling? How long will we continue to benefit from scaling? I think this is a debatable question. I don't know the answer, but I think it's valuable to think about, if the answer is no, why is it likely to be the case? And in today's talk, I'm going to argue that it's likely because the data is fragmented. So what do I mean by data is fragmented? So we all know that for AI training on valuable data that is highly likely to be helpful for AI model is very important. But the thing is, lots of valuable data may not be public. They might not be the public data that is available on the internet. And this is likely to be true, especially with highly specialized domain, which are what today's large language models are focusing on. So some examples include corporate code data. This is internal in corporate, so not public. Some copyrighted books that might be owned by publishers, but you cannot access from internet, or some biomedical data. So these are all the things that are highly valuable for language model capability, but you may not be able to find from the internet. The other thing is, even the data that was once public is becoming proprietary. This is a chart from a really amazing paper called Consent and Crisis. Here they analyze the website from the internet and analyze how permissive the data owner set in terms of using the data for AI model training in particular. Here x-axis is the year, so we can see how this trend changes over the year. The high-level takeaway here is it's increasingly happening that the data owners set their data to be not permissive for AI model training. And this is especially since the release of ChatGPT, as you can see here. So even though some data was once public in internet, now the data owners are closing it up, which is understandable because their data is highly valuable. They may have a commercial benefit or some other, for other competitive reason, it makes sense to not release the data to public. Okay, so that's kind of the idea to explain why the data is likely fragmented, because now it's owned by different parties, different data owners that wouldn't share the data. Now, from an LLM researcher's perspective, the question is, can we come up with an LLM training recipe that can actually benefit from such proprietary fragmented data while respecting data owners? So let's recap how current LLM recipe works to understand that. So how we train today's LLM is we collect all possible data as much as possible. They might be coming from public sources like the internet, or if you're at a company, you might purchase the data. So you'll collect all possible data as much as possible. You randomly shuffle the data and use that to train one big giant model. This works very well, we all know that, but it doesn't necessarily can benefit from fragmented data because it requires centralized access to all the training data that you will use. It has to be in centralized location so that you can randomly shuffle. But it doesn't really support training a single model on fragmented data. So what we want to do is to have a setup where you can build a model collaboratively across different data owners so that we can benefit from these data sets owned by different parties. So we want something like that where one party could be the one who can train a public data, and that could be the largest portion. But if your other data owners like news, publisher or Reddit that have your own data, and you want to keep your data local, then you can still train some component of the model and contribute so that in the end you can still have a combined unified model that is built collaboratively. And this is great because it can be beneficial for both sides. For a user side, the resulting model is still likely to be more performant because it makes it possible to use the data that would not have otherwise be leveraged. And then from the data owner side, you are still keeping each of this data locally, so you never release the data, but you can still contribute to the powerful AI model. So it can be beneficial for both sides. So that's kind of the setup. Now the question is, can federated learning support this? I think the answer to this question depends on what federated learning you're talking about because the definition can be very broad. But let's talk about the conventional notion of federated learning where different parties exchange gradient updates, so you do synchronous training all together. In that case, there are some advantages in LLM training because it does not support flexible opt-in and opt-out. You have to coordinate in terms of logistics to decide when you will gather together to synchronously train this one model. And after this training is done, it's very difficult to opt out for free. All of these are in particular challenging for foundation model because in our setup, it's cross-institutional by nature. Different owners are likely to be coming from different institutions. And its training run is very expensive. So not having flexibility on when you can join and when you can opt out can be quite expensive. Okay, so we introduced this new model class called FlexOlmo that is designed to support this idea. And in particular, it supports modular distributed training. Let me explain the setup first. So we assume we have some base model that is trained on public data that looks like this. Then each data owner can take this public model and bring it to their local infrastructure and train a model component locally on their private data set. And this training happens locally, so you're not sharing the data to anyone else. Once this training is completed, then the data still keeps private, but you share the model component trained on this data back to the public so that we can combine them and make it a single unified model. So you can see this have two unique properties. First, it enables data contribution without sharing the data. You're essentially making data contribution by sharing the model weight trained on the data, even though you're never sharing the data itself. And second, opt-in and opt-out is very flexible. Because each training is completely distributed and asynchronous, you can always opt-in and opt-out. For instance, if the first data owner want to opt-in, they can contribute their model component. You can still merge it into the combined model. If some of them do not want to withdraw later on, we can simply remove the model component contributed by them, and then the rest of the model is guaranteed not to use any data from that contributor. Is that clear? Cool. Okay, so how do we actually build such a model then? So we started with revisiting some of the techniques from the literature, and one idea that came up to us is model merging. So what is model merging in general? So so it means when you have a set of models that share the same architecture, you can simply merge the weight or merge the output, like ensembling, to make it a single output distribution. So in our case, we have a public model and then individual models trained by different data owners. They can share the model architecture. So if we gather together, we're going to end up having 4 different models, and we can merge by doing weight merging, which is called model soup, or by merging the output from individual models, that's called ensembling. So this model merging is actually a very standard technique in LLM training in general. They found training multiple models with slightly different data distribution and merging them post-hoc improve performance quite significantly. So people have been using that. So it was very natural choice for us to consider. So we experimented with that, and we're going to show results soon. But we found that merging models doesn't work quite well in our setup. And in particular, the main difference from how people usually use model merging and us is, in our case, the training data sets of different models are completely disjoint to each other. So when it happens, then model weights trained on those data sets can diverge too much from each other, so the merging becomes very difficult. So yeah, that's a model merging. So the second idea we came up with is MOE merging. So let's start with talking about what is MOE. And MOE is mixture of experts, which is a dominant architecture that industry is using by default nowadays. So this is how the default transformer looks like. It's a dense model that has some normalization, multi-attention, and FFN. Usually FFN is responsible for the majority of parameters, and then we repeat them L times to stack L layers of transformer. That's the dense model. MOE looks like this. Essentially, we break down the FFN into n different number of smaller FFN. We call them experts or expert modules. And then we can selectively activate a subset of them instead of activating all of them. And then there is a router. Router can be seen as an n-way classifier that decides which experts to activate. And this is a dominant architecture in industry because it makes training and inference much more efficient. Okay. So one really important preliminary that we're going to come back for MOE is how this router looks like. So as I said, it's essentially an n-way classifier. So it basically takes the input from the lower layer, the output from normalization, and then there is a router matrix that is h by n. That is a learnable parameter, and then you multiply that to get n-way output. So that's the activation from the model. And each logit here decides how much score we want to give to each individual expert. So if this score is high, that means you're going to consider that the output from this expert more heavily. So we're going to revisit this later, so I wanted to mention. Okay. So that's basically MOE. People use that.
Routing, or is it mixing the experts?
Oh, it's used for both. So they use a router to decide which one to activate. So if they're not activated, they're not going to be used. But they also use the specific weight values to decide how much to weight after expert has been used.
So, but is the routing just zeroing out some of the weights?
Yes. So if it
thresholding some of the weights?
It's usually top K based. So if you have a K value like 8 out of 64, if it's not one of top K, you zero out so that it's not used. If it's included in top K, then you use the weighted average. Cool. Any other question? Yeah, okay, so we talk about MOE, how that look like. People use it for efficiency, but our motivation is, can we use this modular architecture to enable collaborative training? So what we do is as follows. So again, we have...
I guess one last question. How do you ensure diversity amongst the experts? How How do you ensure diversity amongst the experts?
That's a great question. So I can talk about how industry is building MOE. They don't necessarily care about the diversity or specialization.
Serves no purpose, right?
Sorry?
Without diversity, serves little purpose. Without diversity, there is little purpose in mixing the experts.
Okay. Okay. I think the answer is different if you're referring to our model or the industry MOE model. I'll
Don't worry about the question.
Yeah, I can still give you a response. In industry MOE, they necessarily don't care about diversity because their goal is efficiency. What people found is if they analyze these experts, because these experts are end-to-end trained, not necessarily giving bias about how they should specialize, but they can still take these experts, they can see whether they're specializing. They found that there is some degree of specialization, at least in the token level, but not in domain specialization. But we can talk about how our model is different soon. Cool. Okay. Yeah, so I'm going to talk about how we can make use of this modular architecture for our purpose, which is collaborative training. So in our setup, again, we have a public model, the blue one, and then each data owner would continue pre-train each model to build their own expert, and then we want to merge it into an MOE. And in particular, what we could do is to keep each FFN separate, but then the other shared layers like normalization and multi-head attention can be merged through weight merging. And then there should be a way to come up with a router because in mixture of experts, you need some way to do a router. So that's kind of the idea. Architecture-wise, this resulting architecture is same as the standard mixture of experts, even though how it's being trained is very different, which is a great benefit because it means if you already have an inference or serving infra to serve MOE, you can exactly reuse it without needing to change anything. However, it also has some problems. One problem is this model merging of multi-head attention and other shared layers may not work very well because they have never trained in this way. The other problem is this router. We need some way to initialize or set the router because it involves this router matrix that should be learnable. However, we don't have that. So in order to make that work, you need to train the merge model after merging has already happened to actually make it work. Some prior work has made it work. In our setting, this is not really applicable because we want each data set to be sitting privately on each data owner. So you can't really join all these data sets to train the merge model jointly. So now our research question is how can we make it work in a way that you don't need any further training after merging? Cool. Okay, so we came up with a few techniques. One is learning to coordinate, and this is how it works. Suppose you have a public model trained on public data here, and then you're one of the data owner. You have your own data. You want to continue train your model. Then instead of doing typical continual pre-training so that you would override all model weights, you are going to make it essentially a mixture of experts with 2 experts by adding a second FFN. We're going to talk about the router later, so let's forget about router for now. But you can see then it looks exactly the same as mixture of experts with 2 experts. Then we're going to freeze all the shared layers like multi-head attention, and then the first FFN. So the first half looks exactly same as the public model, but then we're only going to train the second FFN. So the impact of this is it kind of makes the second FFN to learn how to coordinate with the public model as an anchor model and learn how to complement that. And other data owners can do the same. Once their training is completed, they only need to share the second FFN, but not the others, because they're already coming from the public model. Then we can merge seamlessly by taking FFN from different data owners and make it as a mixture of experts. This is great because each expert has already learned how to coordinate with the public model, including the first FFN as well as all the other shared layers. And we no longer need to worry about model merging on the shared layers because they're already synchronized.
Sorry, quick question. Maybe I misunderstood.
team has a model, like are the only participants, but it sounds like you also have a public model that's also a participant that allows you to do this where like every organization can sort of train against the public reference. Is that right?
Yes, as we assume there is some central entity who can train a public model so they can serve as an anchor model.
Okay, so the blue is kind of this common anchor.
Yes, yes. Yeah, yeah. Great point. Yeah, thanks for. Other question? Cool. Yeah. So that's how you learn how to coordinate.
So if you use this public model, and I understand that you are trying to sync all the previous layers, but the router kind of only learns to route to two things, not like. So will you do one versus all the way kind of thing when you put the other FFN models there?
I see. So I think maybe you're asking about two things. One is how to train the router, which we haven't gone through yet, so I'm going to talk about it. But I think you also made a good point that even if you only care about FFN, each FFN learned how to work with one other FFN, but not the others. Is that right?
Right, but I think the router training, if you done correctly, might correct for that, I guess.
I see. Partially yes, but that's actually still a challenge. So I think you made a good point. So we are somehow making the assumption that a new expert model that is trained only with another model can generalize when it sees other experts. So that's kind of the generalization assumption we're making. Cool. Yeah, so I talked about how FFN works, but I haven't talked about how router works. So let's talk about that. So as a recap, in the router, the main trainable parameter is this H by N matrix, which we can say router matrix. Our proposal is to decompose it into n different d-dimensional vectors so that each row, each column corresponds to each expert. And each router vector can be contributed by each individual data owner. So we are going to call it a non-parametric router because it's kind of like a retrieval model. So what that means is when your data owner, like New York Times, train their own model, they not only add a second FFN, but they also add a router matrix that consists of two vectors, rpop and r1. And we initialize from the shared domain embedding and freeze rpop, the vector corresponding to the public data, so that they remain frozen, they remain shared across all the data parties. For the corresponding domain router embedding called R1 here, we initialize from domain embedding, but we can continue to train during the training. So in practice, when each data owner trains their model, the trainable part is the second FFN as well as the second router embedding. Once this training is done, then they will contribute this green part back to the public. And now we can merge that into a single mixture of experts model by keeping each FFN separate and then by concatenating all the router embeddings into a single matrix so that it can essentially act like a router matrix.
So maybe this goes back to your industry versus like your question, but what's the ideal behavior the router should have? Do we want it to be sparse in the sense that it only activates something, so inference is maybe cheaper, or you just want a purely better learning mixture of experts type thing? Because when you do this, then it might be hard to make sure that it has some constrained behavior once you combine all the routers.
I see. Okay, so in usual industry model, the idea is to choose the relevant experts so that you can activate it. In our case, I think it's essentially the same. We want to be able to choose experts based on what the user query would look like. For instance, let's say this green expert is coming from New York Times. If a user query is asking something that could benefit from New York Times data, then it would activate FFN. However, I don't think we want it to be completely sparse. We don't want it to be one-hot vector, because in that case, it's not really better than keeping each individual expert and just having one like LLM router that just decide which one to activate. So we want to benefit from cross-domain data. For instance, for some query, you might need both New York Times data or code data, for instance, or some other cases, you might want both New York Times data or some textbooks from publisher. being able to use them jointly could be helpful, which is why we want to use mixture of experts.
Then I'm kind of confused. Once you get this R1 from the first stage and you
Mhm.
put it in the second stage, how do you train the RPub, R1, R2, R3 thing again once you combine them?
So we don't do that. So we don't do any joint training after the merging happens. All the training happens individually, and then once it's merged, it can be used out of the box. The idea here is at least all these router embeddings are coming from the shared domain embedding, so they're roughly in the shared space. And then this R1 is already trained together with RPub, so it already knows how to coordinate with RPub. And then we hope it generalized to n different domains at inference time.
So it's iterative, like R2 knows how to coordinate with R1, RPub.
That is also possible. We didn't do that. Each router embedding only is trained to coordinate with RPub, but what you suggest also can be possible.
Because I guess then the question is, what if they all fire?
Yeah, like what's the behavior? I don't understand the behavior of this module once it's combined, because it was trained to work with just one other thing.
I see. I think that's a reasonable question, and we also showed later that actually the router behavior is not optimal, even though we do this, we use these techniques. But the idea is still, if you train the model with like n routing embeddings, you can generalize to a different number of router embeddings, even though it's larger. So it's a little similar to the retrieval model. If you think about how retrieval model is trained, it's trained on fixed training corpora, but it can generalize to the new corpora because it's non-parametric. Yeah.
Like one naive question I have is, if instead of 3 routers you had 100, let's say, wouldn't the output of the network, the norm of the output and everything just blow up? Because like you have everything activating and then everything activates through the FFN, and then I don't know how you solve it.
Yeah, when the number grows too like very significantly, it can break. Yeah, we actually have an ongoing work that tries to improve that by making the public model mixture of experts. So you already have a reasonable number of routers, so that adding router vector on top of that is easier. But what we found in this particular paper is still it's not ideal, it's not optimal, but it's still generalized to some degree. I can move on. So I'll take one more question.
So R1, R2, R3, those carry over, and then RPub in the combined, is that just the average of the RPubs that you learned with each, or is it relearned on its own?
Oh, no. So RPub is initialized from the domain embeddings, same as R1, R2, and R3, but RPub is just frozen. Yeah, and then when I say domain embedding, it really means when we have each training data, we can get a vector representation from that data. Yeah. I'll get the last question and then move on.
So, okay, I have a question about setup. So,
Mm-hmm.
each institute has trained their own model.
Mm-hmm.
Right? But I feel like, so you don't basically involve in the training, right? In the center. So basically, one institute can overfit their model such that it can mess up the rotor. Is it possible?
I see. First of all, yes. Each training is completely distributed. They can even use their own infra, so we don't necessarily assume there's a central government that decide how they should be trained. That's true. And then I think you made a good point that if one of the participants mess up with their experts or contribute harmful experts, then the combined model can go wrong. I think that's an important practical question, because that means if to use that in the real world, we need some monitoring or validating process that can actually govern who can participate. Cool. Okay, I'll move on. So yeah, that was a non-parametric router. That's all of the technical contribution of this work. So I'll just do a recap with a summary. So okay, we have a model trained on public data only, so it's accessible for everyone. That's the public model. Then individual data owner take it, make it a two-way mixture of experts by adding a secondary FFN as well as making a router. They train this green, yellow, orange part only while keeping the component from the public model frozen so that they're synchronized. Once this training is done, they contribute all the FFNs as well as the router embedding back to the public space, and now we can merge them seamlessly by keeping each FFN separate and by concatenating all the router vectors to make it a single matrix. So again, this is exactly same as typical mixture of experts architecture, so you can use the usual serving or inference infrastructure without needing to change anything. And as I mentioned earlier, one of the nice part of it is opt-in and opt-out is very flexible. If a new data owner wants to join, then they can do that simply by having their own independent training, contribute their component, and we can just add it to the merge model without needing to retrain anything. If one of the data owner want to opt out, for instance, let's say New York Times want to opt out, then we can do that simply by removing the model component contributed by the New York Times, and this merge model is guaranteed not to use any part of New York Times data. Cool. I'll now move on to experimental setup. So coming up with the reasonable experimental setup was quite challenging because we want the setup to be as realistic as possible, but since we are doing it for academic research, we couldn't use actual private data. So we came up with some domains that we think are reasonable in reflecting the real-world domains that are likely to be private. So for public data, we use Common Crawl, which is the internet data. And then as proprietary data sets, we use 7 different domains, including math, code, news, Reddit, and so on. In particular, the 3 domains on the bottom are actually real proprietary data sets that are either once public but no longer public, for like Reddit, or was never public. So they are real proprietary data sets. The ones on the top are those that are public data sets, but we believe that reflect real-world domains that are likely to be private. Like code, there could be a lot of corporate code data. Papers are likely to be owned by publishers, and so on. So these are simulated proprietary data sets. I'll not go over all the details, but we try to experiment with a reasonable scale, not too small scale, so that we can reflect the real world use. Each expert is 7 billion parameters, so after merging, it can be up to 35 billion total parameters. We pre-train the public shared model for 1 trillion tokens, and then we assume each data owner can do continual pre-training on additional 50 billion tokens. Cool. So now I'll talk about the result. So in the paper, we experimented with many benchmarks, like 30 number of benchmarks. But here, I'll just show a result of a few benchmarks, as well as the average number. MMLU Pro and AGI Eval are more of the general purpose benchmarks. Okay. And then Math 2 is an average of 2 math-specific benchmarks so that we can look at the domain-specific number. This is the result of the public model, the model trained on public data only. This is an important baseline because if we do not have a way to incorporate private data, then this would be the model we would have access to. So in some sense, this is our main baseline. Now we train individual experts by doing normal continual pre-training on each individual private data. We show 3 of them here. So what we found is continual training does help in domain tasks. For instance, the math expert helps math tasks significantly, which is expected, but it hurts out of domain. For instance, if you look at how math experts or code experts are doing on MMLU Pro, you can see they drop from public model because they may overfit to a specific domain. However, our goal is still to have a general purpose model so that we shouldn't have this out of domain drop. Okay. Now we compare with prior model merging method, in particular model soup, which do weight merging, BTM, which does output merging, so more like ensembling, and BTX, which is an MOE merging, but prior work that is not using our method. So we can see that the results actually vary a lot. Among 3 model merging methods, we found BTM works the best. especially for MMLU Pro, AGI eval, and the average number. However, all of them struggle significantly to a domain-specific number like Math2. In particular, they are still better than the public model, but we can see we are no longer keeping the performance gain from individual experts. So our goal is, can we keep the number on general purpose benchmark while still getting maximum benefit from individual experts? So now we have our model called FlexOlmo, and we can see it is achieving this to some degree. In particular, we are getting quite a benefit in general purpose benchmarks like MMLU Pro and AGI eval, likely because they do benefit from the data we added, like math, textbooks, papers, and so on. And then for domain-specific benchmark like Math2, we do keep the benefit from individual experts. So on average, we were able to get 41% relative gain. So this is exciting, but there is one more really important question, which is, suppose you could actually have joint access across all the data sets so that you can train one model all jointly, then that model is likely to be better, but how far are we? Like, how much do we lose from that reference model? So we have that model. We call it unrestricted MOE. We also make it MOE so that that's more comparable at inference time, and that number is like this. So this model is better than our model, which is expected, but our model is actually close. Our model retains 90% of the benefit of fully unrestricted training. I think this is quite exciting because that means if you're willing to pay for 10% of the benefit, then you can get other exciting benefit like being able to opt in, opt out later on, modular training, keeping data private, and so on.
How did you actually train the router in this case? Is it the same as the FlexOlmo, or you route with the softmax distribution?
So we just follow those how standard MOEs are trained, which is all end-to-end training.
Okay.
Yeah.
So if I just remove, let's say, one task, let's say AGI eval, I remove the FFN corresponding to that, router corresponding to that, how much does the performance drop for FlexOlmo on that tasks?
Great question. So one quick clarification, we don't necessarily have corresponding experts per benchmark because we think it's kind of like cheating. So we actually don't have a specific expert corresponding to AGI eval or MMLU Pro. Only the math was those things, but we did do the opt-out experiment, so I'll go over that. So yes, we wanted to see, can you actually remove one expert after being merged and see how it works? So in this case, we opt out the news expert and see how performance change. So what we found is on a task called news generation, which is obviously related to news, performance dropped by 10%, which is expected since we removed news data. However, other benchmarks number remain quite same. In particular, in some cases, like math, it can even improve, likely because now there is less candidate for the router, so that the router is less likely to be confused. So it was just to showcase that opting out have minimal impact to other experts and other domains. Cool, okay, so I think that's it. I think we're right on time also, so great. I'll just wrap up with summary. So standard MOS has been used in a standard way, mainly for training and inference efficiency. However, we were mainly interested in how we can do collaborative training when data is proprietary and fragmented because they're owned by different parties. So we wanted to see how we can make use of this modular architecture that come naturally by the MOE architecture and use that. We came up with an approach where different experts can be trained by different data owners, and we can merge it into a single model without needing to do retraining. It had lots of technical problems because generalization to unseen experts was a challenge, but we were able to deal with that in part by MOE-aware coordinated training and non-parametric router. We also show results where this merged model significantly outperformed the model trained on public data only. It can approach joint training on all data, which is the unrestricted MOE. It can also improve training efficiency, actually, because each component is distributed training, so each individual training is much cheaper. And finally, it provides free opting out for data owners who want to withdraw later on. I'll just really briefly go over some open problems. How can we make fine-grained MOE possible with this so that we can have more fine-grained control, so maybe not 8 experts, but hundreds of experts. And then how to scale the number of experts in data set becomes also a challenge. And also, can we use this architecture to allow continual learning? For instance, if you have one model, you want to add new capability later on, can you use this recipe to support that? And finally, how to better train a non-parametric router, because as we briefly discussed during Q&A, this suboptimal router still remains the biggest bottleneck in performance. I'm happy to talk more about that after the talk. And yeah, thanks for listening. If you have more questions, I'm happy to, if you have time. Yeah. I'll get the question.
Is this framework mostly for pre-training or post-training?
That's a great question. It was mainly for pre-training. This paper focused on pre-training, although we are currently working on how to make it work for post-training. And post-training is interesting because it adds an additional challenge. In particular, your base model, the public model, is likely to be fully post-trained model, and then you should be able to add new data, which might be pre-trained model. So you might have to go back to pre-training, even though the base model is already post-trained. So it kind of have these additional challenges that is likely to be a very realistic. Yeah.
So these evaluations that you showed, like coding and math, all of these are evaluated without any post-training?
Yeah, they're all pre-training evals. We use in-context learning so that the model can still do the task without being post-trained. Yeah, I think there was another question.
Is there any chance of contamination in test data? Like when you introduce experts, is there any chance they have seen data that is in the test data?
That's a great question. So we took the pre-training data that was created by others. For math, we use open math text and fine math, which we believe that the original author is contaminated with popular benchmarks. But I think it's a good thing to check. Yeah. Oh, yeah.
So if I understood correctly, in the first part, the aim was to learn these previous modules before the router, sort of in conjunction with the public model.
Mm-hmm.
So these are trained, right? Indeed, during the first phase. Might get attention and everything else, or they are somehow frozen from some pre-training, or.
You mean when data owner do their training? All the shared layers are coming from the public model, so we keep it frozen.
Okay, so you never actually.
We never train. Yeah.
So you get really formal unlearning when you remove the user actually, then, because there's nothing from the user.
Yes. And actually, that's a good point that we did some ablation on how much we lose by freezing self-attention, and we found even when we don't care about collaborative training, it actually doesn't drop the performance so much. I think it's likely. I think there's some explanation from the community that FFNs are mostly responsible for new knowledge, and self-attention is more like how to read the context, which is more general capability rather than specific knowledge, and that might be why adding the FFN helps, but shared layers are okay to keep frozen. Oh, yeah.
So your centralized model that is fully MOE, trained on the full data, it's not sparse MOE, right? And the output of your framework is also not sparse MOE, right? So it somehow weights the router is fully connected layers of experts, right? And it doesn't do selection of top K.
We actually still keep it sparse in that we still keep top K. For instance, in our final model, we activated 4 out of 8, which is actually a little less sparse than typical MOE, but it's still sparse. I think it's more like a design choice.
So you say that you do sparse for both for centralized training as a comparison and sparse for the framework that you use?
When you say centralized model, do you mean the upper bound model?
You use centralized learning for instead of doing the iterated or distributed, the one that you use all the data at the same time.
Yeah, the unrestricted MOE.
Sparse, right?
Yeah, so we.
Both of them are sparse.
Yeah, so we keep the same hyperparameter. I believe both of them use activated 4 out of 8 experts. Yeah. Yeah, then I think that's it. Yeah, thanks for listening. Oh.
Like
Oh.
does it normalize, like when you have routers, like do you normalize them by like do they end up to some kind of number? Like when you do router like multiplication by the layer, do you normalize it by the sum?
I see. Let me think. Okay, so I know it's zero odd if they're not top four, so they are zeros. Among top four, we keep the weights so that when we do like MOE, they will do weighted averaging, which is like a standard practice as MOE. I actually don't remember if we normalize after zeroing out. I believe even standard MOEs have different practices depending on which model. I know some models do renormalize, some models did not renormalize. We probably follow like one of them, yeah. Cool, yeah, thanks. Do we have time to?
Oh, yeah.
Okay, I'll get the last question, yeah.
Do you normalize the outer norms of the R vectors in the vector?
Oh, we normalize. That's a good question. I don't think we normalize them, but I think they naturally are already in the similar norm value because we all initialize it from the same domain embedding. Yeah. Cool, yeah, thanks for listening.
Okay, thank you, Sewon.